there's lots of lift at this angle step, and that's a result of basically it's a result of two factors: the viscosity of the fluid and this big inverse pressure gradient, and that's what I mentioned before. We get along our airfoil when it's doing this lift up here. So we need to think about boundary layers and know what boundary layers are for this. If you think about a fluid and a solid, the fluid has some friction with that solid where it touches the solid, right? And so the fluid where it touches that solid does not want to move, it wants to stay still, because friction's holding it in place. And so you can see if you have no flow or constant flow all the way along, no flow in a situation, the fluid is going to sit still. As we increase the speed of our fluid, you can see the bits that are in the free stream start moving in the free stream, but the parts by the wall still stay still. And then you get this short region between the two, where the fluid is going from stationary at wall to the free stream velocity. And as we move on and increase the speed yet more, we can see now this area here is still moving free stream velocity, but we're still not going anywhere at the wall, and we have this region in between where we're transitioning from zero velocity here up to the free stream velocity up here. And this region from there to there, that's what we call our boundary layer. Our layer where we're moving less than 99% of the free stream velocity. So this little diagram of that is this velocity is 99% of free stream. Anything below that, anything going slower than that, is a boundary layer. It's stationary at the wall, and so those provide our two limits where our boundary layer is, where it's at zero at the wall, and where it's at 99% off boundary layer of the free stream velocity at the edge of the boundary layer. And that provides us some thickness to the boundary layer, using delta here. Boundary layers form as a fluid, like you mentioned, it's just like an empty area, and then it starts being solid. As it goes down the solid, boundary layer height increases as the larger and larger amount of fluid is decelerated by the inner viscosity. By the viscosity of the fluid or its inner frictions of itself. So as we start out here, only bits very close to the wall overflow. As we go down, further down the wall, further down the wall, more of the fluid is decelerated by the friction of the fluid, by the viscosity of the fluid. And the region where the fluid is going slower, i.e. less than 99% velocity, gets bigger and bigger as we go downstream. Okay.
Sorry.
So that was our boundary layer forming on our flat plate, right? Flat plate on the flat surface. You can now imagine that same thing's happening along the curved top surface of an airfoil. Right? So imagine it's the top of your airfoil, you've got the leading edge up here, you've got your trailing edge down here. Right? As the fluid flows over the surface, we're going to get our boundary layer start to form, where it's slowed down by friction of the wall, and then slowed down a little bit away from the wall by viscosity. As we go down the wing, we're going to get a boundary layer getting bigger and bigger, and bigger, right? But there's another force action on the fluid here, rather than just the viscosity of the fluid, rather than just the internal frictions. There's also our adverse pressure gradient, right? So if you imagine a little volume of fluid, right? We've got this side AB, AC, and BD, right? Which of these sides, AC or BD, do you think has a greater force acting on it? AC. Why AC? It's close to high pressure here. What's the pressure here? No, is it very... Is it high pressure or is it low pressure? Yeah, very low pressure. Okay. What is it? Higher pressure, right? Yeah, so less low. That's a higher pressure. Okay. So that means because we've got higher pressures at this point here, so it's less low. The force on the fluid is that, which means that this BD region is closer to our higher, i.e. less low region of pressure, so the force on the fluid is this one. So this BD region experiences greater force than the AC. So as we come down this way, we're getting more and more force backwards from the fluid, right? Trying to decelerate it against the way we're talking about. Caused by the pressure generated by the reform of the wheel. As we get further and further down the lane, that force gets higher and higher, and eventually it acts to decelerate the flow so much that it's not just the flow touching the wall that's stationary, but also the flow starts to fall back off the wall. Right? And when that happens, that's what we call separation. It's called boundary layer separation. And where that happens is our point of separation. And as you continue down, more and more of the flow is stationary away from the wall rather than just at it. Right? Parts of the flow start to go backwards, and you have this big separated boundary layer where there's basically no flow relative to the surface. No fluid velocity to the surface in this region. So it's all been decelerated by this pressure gradient, force on the fluid, as well as the viscosity and the friction. So between them, the fluid is all slowed down. And we have this region near the wing, but not touching the wing. It's already zero velocity here, but now there's zero velocity at some point. And when we've got the separated flow, because this velocity isn't really moving, because this fluid isn't really moving relative to the wing, it doesn't generate any pressure, because that's what we mentioned before. The reason the wings generate lift is because the flow is going faster at the top. If the fluid isn't moving over the wing, it's not generating any lift. And so from this point downstream to the trailing edge of the wing, there's no lift being generated by any of this part of the wing. And you can notice that happening here, where right here we have our zero velocity at the wing, but some amount of free stream velocity away from the wing. As we go down the wing, we can see that the region where there is zero flow is a taller and taller region up the wing until it's all the way up to there. And that trailing edge there. So bottom. And then if we really increase our angle of attack, you can see that even right up here, kind of near the bleeding edge, all of this flow is stationary. All of this flow. Now it's going backwards. Right? So none of this part of the way here is doing any lift at all. None of this is what you're seeing. This is just there. Only this very leading edge part of the wing is actually generating lift. And that's why, as we increase more and more angle of attack, eventually we lose so much of the wing to boundary separation that it's no longer increasing the angle of attack doesn't, while it gives us more pressure generated by this tip of the wing, so much of the wing is not doing work that we lose lift by increasing the pressure. And now a big factor that plays into this is the Reynolds number of the top. Reynolds number, you've looked at it before by now, but a good way to think about it is a ratio of the internal forces in the fluid to the viscous forces. So you can think about this as the inertia of the fluid, right? It's its mass times force, right? And so the more inertia the fluid has, the easier it can resist the force on it, just like F equals ma, right? The more inertia the fluid has, the easier it resists the force against it from the pressure. So the further down the wing the fluid, the separation point goes. So rather than having a separation point near the tip, the inertia of the fluid allows it to stay attached further down the wing, and the separation point happens close to the trailing edge. And that allows us to keep our linear region for higher and higher angles of attack, because the fluid has more and more inertia, which resists boundary separation. And that's why, if we look at these low Reynolds number cases, when we have still happening a lower angle of attack, and as we increase our Reynolds number, we can resist that still happening to higher and higher angles of attack. I believe that's all I've got to tell you. Any questions?